Morning, guys. Hope you had a great weekend. Um, I did not get any questions about the test, so I assume you just understood everything. Um, I need those turned in today. You had 5 days to do them, so no grace period there. Um, Good morning, Garrett.
Hi.
And we have a black background now, thanks to Kevin. Um, so I was just saying I need the test turned in today.
I have a question.
Okay.
Could you possibly help me? Or no?
Why are you waiting till Monday morning to ask me this?
Uh, I tried to figure it out and I can't.
Okay, I can help you. With how many do you have?
Um, 2?
Okay. Give me the first one. The number.
18.
Okay. All right, 18.
Actually, 17. Sorry.
That's okay. All right, 17. So let's see. It says if 345.1 grams of CO2 are placed in a vessel whose volume is 32.1 liters at a temperature of 20 degrees Celsius, what will the pressure be? So we're going to list out all the information we have to help us determine what equation to use. Did you figure out what equation yet, or you want to start there?
Uh, is it the ideal gas law?
I'm trying to remember if that's what it's called. Yes, it is the ideal gas law. So really, you just need to convert to the correct units for each thing and then solve for pressure. So our equation is PV equals nRT. So to solve for pressure, I'm just going to divide by volume on each side. And then we'll just plug it in. So first of all, they gave me moles. So, grams.
Have to convert.
Yes, I need moles. So I'm going to go 345.1 grams, and that's CO2. And then we look at the periodic table to find out how many grams in a mole for CO2. Let's see. And it looks like 44. You know how to do that, so I'm not going to get into too much detail. Okay, so that gives me 7.84 moles. So now I have N, this is N right here, the number of moles. And R is that constant. And then the temperature they gave me was in Celsius, so I got to convert that.
20 degrees Celsius, so it's 293 Kelvin.
293? Okay. 0.15?
Yeah.
Okay. And then volume was 32.1. Okay, so we're just going to plug it in. So P equals N, which is 7.84, times R, which is 0.0821, times temperature, which was 293.15, and all of that divided by the volume, which was 32.1. Okay, so then we put that in the calculator. You should get 5.88, and you'll know your unit because for this is moles, and then your unit for R was liters times atmospheres divided by moles times Kelvin. And so everything else will cancel out except for atmospheres. So you know your answer is going to equal 5.88 atmospheres.
Okay.
What part
Where
was off?
Where does that 0.821 come from?
This is a constant. It's R. It's a constant number that
Okay, yeah.
you're supposed to memorize, I guess. It's on page 403. It's the ideal gas constant. It's just a number that you have to know.
Okay.
Was that the part that was throwing you off?
Yeah, I had all the numbers right. I just didn't put them in the right order.
Right.
Constant.
Yes. Okay. Well, I'm glad. If that was all that was tripping you up, you're doing good. Is there another one?
And yeah. And then 18.
Okay. Let's see. Iron rusts according to the following equation. If 1.4 liters of oxygen were added to excess water and iron at a pressure of 0.97 atmospheres and temperature of 55 degrees Celsius, how many grams of iron would rust? So what I first noticed is that they gave me a chemical equation, which usually means I'm going to use stoichiometry. And then I noticed that's correct because they gave me liters of oxygen and asked me for grams of iron. So I'm going from one substance to another substance. So always stoichiometry when I'm doing that. So first, I'm going to have to find, if you want to use stoichiometry, you have to find moles. Can you hear me okay? It feels like it's cutting out.
It a little bit. It's not that bad.
Okay. So first I need moles. So I have liters of oxygen and I have pressure and temperature. So if I have all those things, I can find moles with the equation that we just used. So I'm going to solve for the number of moles over here so I can figure out how to plug it in. Whoops. So number of moles is equal to pressure times volume divided by R times temperature. Cross that out. Does that make sense?
Mm-hmm.
Okay, so let's plug it in. So N equals, the pressure they gave me was 0.97 atmospheres times volume, 1.4 liters. Oops, sorry. Okay, and then all that divided by R, which is 0.0821, and that's liters times atmospheres divided by moles times Kelvin. It's a weird unit. And all that times temperature, which I need to convert, so 55 Celsius plus 273.15 gives me 328.15 Kelvin. And I'm just going to plug that in. Okay. So now you're just going to put all this in the calculator to figure out how many moles you have. So all of this is going to go in parentheses, and then all of this is going to go in parentheses. So in your calculator, it looks like this. You have, open your parentheses, 0.97 times 1.4, close your parentheses, divided by, open a new parentheses, 0.0821 times 328.15, close your parentheses. And that should give you 0.050. And that was moles. We were solving for N right there. So this is moles of oxygen. Okay. So now we have moles of, let's see. It says that the oxygen was added to excess water and iron. So we know oxygen is our limiting reactant. So since we have the number of moles of the limiting reactant, we can go straight to what they're asking me for, which is iron. So let's see. Then I'm going to use stoichiometry. So I'm going to go, my given value of moles, 0.050 moles of O2 over 1. And then I'm going to use that equation they gave me and look and see. So I'm going to iron, which is Fe. And in the equation, I have 4 moles of Fe. So that goes on top. And then I want moles of oxygen to cancel. And in the equation, I have 3. So that's going to go over 3 moles of oxygen. And then you're just going to plug that in the calculator. Whoops. And that will give you 0.067 moles of iron. But you're still not done because they asked you for grams. So now you get to convert that to grams. So I'm going to erase a little bit. All right. So now I have my given value of moles, which I just found, of iron over 1 times, it's going to be 1 mole on the bottom because I'm trying to get moles to cancel. And then I look at the periodic table and find out how many grams in 1 mole of iron, which is 55.8. And once you multiply that, you will get 3.7 grams of iron. Was that too fast? Did you have questions?
No, I kept up.
Okay, cool.
Okay.
That was a 12-point question, so make sure you get all that. How'd you do on 19? Did you figure that one out? Because I think it's similar.
I don't think so. Look at the one we just did.
You want to do it?
Sure.
Okay. I'm going to clear this out. All right. So 19. In 19, they give me grams of magnesium, and they're asking me for pressure, and they're giving me a volume and a temperature. So because there's an equation, and they're asking me to go from one substance to another, because they gave me grams of magnesium asking for pressure of oxygen, I know I'm using stoichiometry. So first, I need to find the moles to use stoichiometry. So I'm going to convert that grams they gave me of magnesium to moles. So first, that's my first step. And I'm very familiar with how to do that. So your grams over 1 times, let's see, 1 mole is going on top, 1 moles. And then you look at the periodic table to see how many grams are in magnesium, 1 mole. And you should see there are 24.3 grams. And once you multiply or divide that out, it'd be 1.3 divided by 24.3. You'll get 0.053 moles of magnesium. Okay, so now we have that. Let's go back. So now we need to find moles of oxygen, because that's what they're asking me for. So let's see. We are going to use stoichiometry now. So I'm going to start with that. Oops. I'm going to start with the moles I just found of magnesium and convert to moles of oxygen. Use the equation, the chemical equation. I want moles of oxygen on top, because that's what I'm going for. And there's just 1 mole in the equation. And I want moles of magnesium on the bottom. And there's 2 moles of magnesium in the equation. So it's going to be in your calculator 0.053 divided by 2. And you'll get 0.027 7 moles of O2. Okay, so now we have, they're asking me for pressure of oxygen, and now I have moles, volume, temperature, and then we know the R constant. So we're going to use that same ideal gas law to solve for the pressure. Okay, so we're just going to divide by volume to get pressure by itself. And then I do need to convert some pieces because I have milliliters instead of liters, and I have Celsius instead of Kelvin. So let's go ahead and convert the volume to liters. So they give me 10 milliliters. And I know in 1 liter there are 1,000. So 10 divided by 1,000 is going to give you 0.01 liters. That's going to be your volume. And then we'll do 25 degrees Celsius plus 273.15. And that's going to give me 298.15. Okay, so now I should have everything I need. I'm just going to plug it in this equation right here. So P equals the number of moles, which was 0.027 right there. Oops, I don't know why I did O's. 0.027 moles times R, which is 0.0821 liters times atmospheres divided by moles times Kelvin. I hate when it does that. I'm going to leave out the unit for now. And then temperature, which was 298.15, close the parentheses. All that divided by volume, which is 0.01 liters. If you were to figure out all your units and cancel them out, they would equal atmospheres. That would be what you're left with, of course. So that equals 66 atmospheres. Any questions on any step there?
No.
Okay. Makes so much sense whenever I talk about it, doesn't it?
Yeah.
I think the main thing with this chapter or module with having so many different equations was just figuring out what you need to use based on what they're giving you. So it just requires a lot of practice. Was that the only questions you had on the test? Now's your chance.
I have one more.
Okay.
I just I did right.
Okay.
Number 13.
Mm-hmm.
Can we go over?
Yeah, we can. Okay, so a balloon is filled with 34.6 liters of helium at 24 degrees Celsius, 1.02 atmospheres. Okay, and then the surrounding temperature decreases and the pressure does too. So the balloon reaches an altitude where the temperature is 11 degrees Celsius and the pressure is 0.21 atmospheres. What will the volume be? So first, what I'm noticing is they're giving me a volume, a temperature, and a pressure, and then they're giving me a new temperature and a new pressure and asking me for a new volume. So I know that's going to be the combined gas law. So P1, V1, I just have to write it this way first so that I can. So P1, V1 divided by T1 equals P2, V2 divided by T2. Oops. That's my equation. So first I need to figure out what they're asking me for so I can solve the equation for that. So they're asking me for the new volume. They're asking me for V2. So what I'm going to do first is go ahead and change this up so that it's equal to V2. So I'm going to multiply this whole side by T2 divided by P2. Because when I do that, P2 will cancel and T2 will cancel, which means I have to do the same thing to this side. So I'm going to multiply this side by T2 divided by P2. I'm sorry that that looks confusing. So the new volume is going to be equal to the new temperature times P1 times V1 divided by the new pressure times T1. Does that make sense how we rearranged all that? We just used algebra.
Yeah.
Okay. All right. So now just basically plugging it in. And the units here don't really matter as long as they're the same units for pressure, volume, and temperature throughout. So it looks like they started with liters and Celsius and atmospheres, and that's the same throughout. So I don't need to convert anything. I just need to plug it in. So T2, so let's see, new volume equals the second temperature, which was 11 degrees Celsius, times the original pressure, which was 1.02 atmospheres, times the original volume, which was 34.6. And all of that is going to be divided by the new pressure, which was 0.21 atmospheres. I'm going to add a parentheses, times the original temperature, which was 24 degrees Celsius. And then you're just going to put all that in your calculator. So don't forget in your calculator to do a parentheses, multiply all this, close it, divided by new parentheses, multiply all that, close your parentheses. And then after you do that, you will get, I'm just using the answer key to save time. 13. Looks like you would get 160 liters, but they converted it to scientific notation. So you could put either 160 liters or 1.6 times 10 to the second power liters for significant figures. But either one is two significant figures, so I'm fine with either answer. Looks like they did convert to Kelvin. I'm not really sure why they did that. Let me make sure I get the same answer because I don't want to tell you wrong. Let's see. 11 times 1.02 times 34.6. Ooh, you don't get the same answer if you don't convert to Kelvin. So, oh, we do have to convert to Kelvin because we can't have a 0 on the bottom here. I forgot about that, but I'm sorry. I just told you wrong. Totally wrong. Okay. So here we're going to have to convert this one and this one. So you would just add 273.15 to each of those. Then it's going to look like this. I apologize. It is Monday. So for our first temperature, we will get 284.15. And then for our second one, $297.15. Okay, so let's try plugging that in. Yep, and that gets you the right answer. I apologize. Okay. So convert to Kelvin always because we can't have a 0 in the denominator. Okay. Did that make sense?
Mm-hmm.
Okay.
Okay.
Any other ones?
No, it was just the back page that I need some help with.
Yeah. So we did 17, 18, 19, and 13. So 12, 14, 15, 16. How are we feeling about those?
15 and 16, I think I'm good.
Okay. Yeah, those are pretty easy.
Uh,
Mole fraction.
I just used like the practice problems that we did, and like
Mhm.
referenced that and plugged in the numbers.
Yep.
And then 12 and 14 are the same, like 13.
Yes. Just don't forget to convert to Kelvin. Lesson learned. Okay. Yeah, so you should be good with those. All
Okay.
right.
Thank you for helping me.
You are welcome. Next time, don't forget I'm always available on the weekend too. Okay, so we're just going to move on to module 12. And you can send me your test today. Anyone else who's watching, make sure you send it to me so I can grade it for you. And today's class should be pretty short because we're just talking about, you have your book with you?
Yes.
We're going to go over pages 418 through 422, and there's no practice problems, so we're just talking. So this module is about energy, heat, and temperature. I found this section pretty interesting. So it's going to kind of walk us through like the scenario of looking at a fire kind of throughout this whole like introduction. So, you know, everyone's seen fire before, but we're going to kind of delve into like what happens to the wood, why is there ash, where does the heat come from, what makes the flames, all that kind of thing has to do with energy and heat and temperature. So we're going to kind of talk about all those things. So a lot of it has to do with chemical reactions, which is the basis of chemistry. And the details we'll talk about later, but first we're going to focus on the flames. So how did the flames appear? Well, flames are a form of energy, and whatever matter undergoes a chemical change, that change is accompanied by either a release or an absorption of energy. And we kind of talked about that briefly a couple modules back because we were talking about when the energy is released, the color of the flames, and I know we talked about a couple different things there, but flames are a form of energy. So first you need to know what energy is. And on the top of 419, it tells you that energy is the ability to do work. In order to know what that means, we need to know what work means. Work is the force applied to an object times the distance that the object travels parallel to that force. So the definition of work says that if you are going to have work occurring, there has to be motion. So you can't have an object travel a distance and the force be 0 because it would be 0 work. So a literal example of that would be pushing against a wall with all your might and the wall doesn't go anywhere. So even though it feels like you did work, you didn't do any work because the wall didn't actually move. So there has to be motion for there to be work. And based on the definition of energy, then, the flames in a fire must be able to cause motion. So how do flames in a fire cause motion? Well, first you see smoke rising up out of the fire. The energy in the flames is causing that motion of the smoke. Also, if you put a pot of water on the flames, then eventually the water is going to boil. The energy in the flames are causing the water to boil, causing the motion in the water. And also think about the heat that you feel when you sit near a fire. The flames are causing that heat to go towards your body. So flames are a form of energy. They are causing motion is what they're trying to get you to see. And while we're on the subject of heat, we'll go ahead and define that. The only way that heat can get to us is by traveling. So like it said, the flames are causing that motion of the heat traveling to our bodies. And you'll see there on 419 the definition of heat. energy that is transferred as a consequence of temperature differences. So let's see. If energy is the ability to create motion, and if we use heat from a fire to boil water, the heat would be creating motion. So therefore, heat must be energy as well. So flames are energy and heat is energy. And heat is a special form of energy. It is always on its way from a hot body to a cold body. It always travels from hot to cold. So if there's no difference in temperature, there is no heat happening, which is kind of common sense, but they say it anyway. And I'm moving on to page 420. So we know a fire is sending out heat because we can feel it, but we don't really know where it came from. So the question is, where did the energy that's causing that heat first come from? Well, first you have the wood sitting there. You have oxygen in the air around the wood before your fire starts. You have all this sitting there. Well, the wood and the oxygen around all have an enormous amount of energy in them just sitting there. So why doesn't the wood feel hot when we touch it? Or why don't we feel heat coming from it initially before the fire is lit? That's because the energy is stored, it's trapped, and it can't be transferred until the wood is burned. So when the wood burns, the energy that's been stored is then released and transferred into heat. And that's what we feel. So this leads us to probably the most important law of science, which I'm sure you've heard before. The first law of thermodynamics is that energy cannot be created or destroyed. It can only change form. So like we said, that wood was sitting there, that oxygen was around with energy stored in it. It just wasn't released until you caused that chemical reaction of the actual burning of the wood. So this law tells us that God only made so much energy for the whole universe. We'll never be able to create it. We're not as smart or as powerful as he is. So it makes sense that, we're not able to create it or destroy it. So the energy, we're not making energy when we start a fire. We're just releasing the energy that was already stored in it. So let's see. That leads us to the two types of energy. So you have potential energy, which is energy that is stored. So that wood sitting there had potential energy, just waiting. And then you have kinetic energy, which is energy in motion. So once the fire was started, the potential energy just changed forms into kinetic energy. So no energy was created. It was just changed from potential to kinetic. Heat is considered a type of kinetic energy because heat has to transfer from a hot body to a cold body. So if it's in motion, if it's moving, that means it's kinetic energy. Let's see. And they did want to point out, which I thought was interesting, that all substances have energy stored in them. So all substances have potential energy in them. Okay, so moving on to 421 units for measuring heat and energy. First, we will talk about the unit for energy. It's called Joule, Joule, excuse me, and it's named after a scientist named James Prescott Joule, and he was a devout Christian, which is pretty cool. A lot of the chemists we talk about, or scientists that we talk about in the book, were Christians, which is kind of interesting. He did a lot of research on energy, and so they named the unit after him. And in that little green section, the salt and light, it tells you more about him. And I just thought it was really cool because it gave a couple little fun facts about him. And it said that he approached research with the belief that all of creation should be understood with simplicity, and his experiments were designed with that in mind. But he was so smart. He was the first to develop a conversion factor between heat and mechanical work, which led to the development of the first law of thermodynamics, which is like one of the foundations of science. So he was a brilliant man, and he served the Lord. So that just kind of shows me that like science and God can go hand in hand. But going back to the unit for a joule, for energy, joules. So a joule, 1 joule, is the energy that you need to lift a 102 gram object straight up for 1 meter, that would take 1 joule of energy. So to put that into like a visual, a paper clip weighs about a gram. So 1 joule is the energy you need to lift 102 paper clips in the air at a constant speed, just a little bit higher than a yard, because that's about a meter. So it doesn't seem like a lot. 1 joule, you wouldn't need too much energy to do that. But that's going to be the unit we measure in for this module. So when in potential form, energy is really hard to measure, as you can imagine, because it's stored. But it's pretty easy to measure kinetic energy. So a lot of this module is going to be spent on measuring heat by using temperature. So then you also need to know that temperature and heat are not the same, but they are related. So then if you flip over to 422, it talks about how we measure heat with a thermometer. It gives you a little bit about a thermometer. A thermometer is, it measures heat based on the fact that substances expand as they get warmer. So when you have a thermometer with the mercury in it, when it gets warmer, it expands, it goes up because it's in a column. So that's how they're measuring the temperature, which means that they're really measuring temperature indirectly, which is the way we do a lot in science. So just kind of interesting. And then that whole experiment in 12.1 was just talking about thermometers and how accurate they are and all that type thing. So we're not going to do that one because it's just a whole lot of, to me, it's kind of busy work, but they're just basically wanting you to see that thermometers measure temperature indirectly. Some are more accurate than others based on the style of the thermometer. So that's how we'll measure heat. And yeah, that's basically all we had for the introduction to the chapter. And did you have any questions or comments on all that? Energy, heat, and temperature?
No, not really.
Well, that's all I had for today. Tomorrow we will, looks like we'll talk a little bit more about some other units and some more measuring, and then we'll do a couple examples with all of that. So we'll do that tomorrow, and just send me your test. Make sure the pictures are clear so I can read it. And thanks for coming to class. I really appreciate you coming. It makes me feel like I'm not weird sitting here by myself. All right, well, have a good day. I'll talk to you tomorrow.
Yeah.
Bye.